Okay. Um, all right. A couple of bookkeeping notes here. No class on Tuesday, if I'm uh, reading the academic calendar correctly. I believe that's a wellness day. And also, this will cover um, uh, channel models a little bit today, and then we'll meet again on the following Friday. We do have I think there was an assignment due earlier this week, and now we've uh, ready to move on to the next assignment if I've got all my timing correct. So uh, it's having problems with the remotely service, and so when I try to log into lab computers remotely, I'm not having actually any options to do that. So I went ahead and did an Octave version of um, the assignment on source encoding. So that's Octave is an free open source software that tries its best to emulate MATLAB. That's a crude way of saying it, I guess. But I have that installed on my Mac. My MATLAB version is so old it doesn't run on the new Mac. So this it uses the same syntax. There's a few little differences here and there, but I'll point those out as we go along. So I think what are we doing? We're doing Huffman encoding, right? And we're using the built-in functions to do that. I'm not asking to build the tree manually yourself and search over it and that type of thing. So we'll just use the built-in functions. And so first you'll use some symbols that I give you, 0 through 6, with some probabilities, and then I'm asking you a few questions, and then ask you to go ahead and encode it, and then decode it, verify that the output result matches the source symbols, right? So if we encode and then decode, this is a lossless compression approach, meaning that we should get back exactly what we started with, right? So that's in contrast to a lossy type of thing, like let's say a JPEG encoder for images, right? So that is compressing, but as it does it, it's actually kind of reducing the image resolution and quality via some trade-offs, right? So, but the things we talked about are lossless. So we should get back exactly what we did, and then so we do it first with kind of a finite set of symbols, and these should all be within the alphabet, right? But this is, I think, 20 symbols long, and then you're going to repeat it, but use like 10,000 symbols, and we're going to generate those randomly, and then at the end you'll calculate the entropy and the average rate, right? So let's look at that real quick. I can't remember actually if we looked at this on Tuesday, but we'll do it again here real quick because we got a lot to cover today. So symbols, just use the notation that MATLAB Octave have to just generate a sequence, integer sequence, 0 to 6, and then I put the probabilities into an array. Remember, in MATLAB, you don't put any commas here. This would produce a kind of a row vector. And then we create the encoder, right? So we use the Huffman dictionary, Huffman-Dict. We pass it the symbols and the probabilities, and it's going to build that tree that we do, which may show up on the final exam, and how you kind of order things in terms of probabilities, and you work your way through that tree, assigning the codes to it, right? And so that's all done in this encoder, using a Huffman-Dict. And then we'll calculate the number of bits that we would need to represent the symbols without source coding, right? And so that would basically be, did someone message me? I don't see it. Okay. So that would be basically, if we don't do any encoding, how do we represent this alphabet of symbols? Well, it's going through from 0 to 6, so calculate the number of bits that would need to send any and all of those symbols, right? And then we give you a set of source symbols. And here there's a difference with Octave. In the MATLAB case, you can just pass in to the encoder the source symbols here, the source symbols themselves, right? Yeah, I think this is correct. I don't haven't verified this, but when I did it before, I think this is what I was using. So you can pass in the source symbols and the encoder, and it uses the encoder to encode these source symbols and return back their code. The Octave way of doing it, some of this is done internally in MATLAB. I mean, these steps have to happen, but they're inside. So what we do first is we use this isMember thing. We look up the source symbols in the alphabet, and one of the second parameter returns is the index of each of these in the symbols, right? So the symbols is going to be represented as a vector. So what this would be doing is it would be finding the position of each of these in this, right? So like a 0 would be in the first position of this. So that since MATLAB and Octave use ones-based array indexing, right? It doesn't start at 0, starts at 1. And so that would be an index of 1, right? A 1 would be an index of 2, right? So that's what it's returning here in the source index. And then when we encode it, we pass it that source index, and it's going to return back the codes. So, and then the other thing we'll do here is we'll create this large signal, and here we'll use the function rand source, and we pass it n comma 1, so we want n 10,000 by 1, right? So we want a vector of these, not a matrix. And then we pass it the symbols in one row, and then this semicolon says, well, these brackets, square brackets, says make an array out of this, matrix out of it. And symbols is the first line, the first row, and the semicolon separates to a new row. and the probabilities in that new row. Then this would return, I think a column vector. So we want to do a little transpose there to keep it as a row vector, so we're consistent with things, and then go through the same steps. And then we also, let me go back up here. So we decode it, and then in Octave, I'm this Huffman decoder will return back the index. So then I dereference that using symbols and pass this in as an index. You don't have to do that in MATLAB if I've done that correctly. So so now we have decoded, and we're going to use is equals in this case. Lots of different ways of doing this. You could do an element by element comparison, as we've done before when we compare bits, input and output bits. Here we're going to use is equal. We're going to pass this vector and this vector, and it will return back a single value, Boolean value, right? And so then and you can do this in a lot of different ways, but I set a result based upon this if statement, right? So I either say that it's the same as or different from, and then I print out that result. So the decoded rate results are, and I format result as a string, the source symbols, right? And so on. And then, all right, down here, I calculate the entropy. Just be aware that when if you try to look up the entropy function in MATLAB, that's a different kind of entropy, right? So entropy is used in a few different ways, and the built-in function for entropy in MATLAB is not going to do what you think it does. So just calculate it directly, log base 2 of the probability, but then we really want the average. So we're going to element by element in here, multiplied by the probability. So this is with the minus sign here, this is the entropy, and then we weight it by each individual probability, and then we sum those up, right? So that's how you would calculate the mean value, right? So, and then I print that out, and I'm printing out the question number each time here, so it makes it easy for me to see what you're doing. And then calculating the average length. This is a little tricky. I'm not sure that this is exactly the same way as you would do it in MATLAB. Probably pretty close though. So let's just initialize an average length to 0 and then iterate through all the symbols, right? And with defining an index 1 through the length of that symbol vector. And in each case, I'm going to look up the value in the encoder. That's that dictionary that we built. And then that's going to actually return back a cell. Then I'm going to get the contents of that cell here. And then I'm going to, that's going to be like a 1 or 0, 1 or that type of thing, right? And then I'm going to just calculate the length of that, because in the Huffman encoder, it's variable length coding, right? So we're going to look at the length of each code word, multiply, weight it by the probability of that particular symbol, right? That probability there. And then basically accumulate that, sum that up in average length, and then just print that out. So you see down here, these are my answers. If you do it in this way, that's, you're essentially meeting the requirements of the report. So as long as your code runs, that would be sufficient. But you should probably just cut and paste this and dump it into a a very minimalistic report. Right. So hope that helps. And let's see, when is this? This is due on Tuesday, Tuesday at midnight. So I think that's reasonable. And I haven't created one on Spread Spectrum yet, but I will shortly. And so let's see, we're here on Friday 18th, and we're going to look at fading channels, and then we have the day off, and then we just have, I think, 5 more classes. But because we missed a class back here, did I not spell that right? Then we need to make that up, and I'm just going to post a thing on standards and research trends and communications. I'm going to record that shortly, and I'll post that, and you can watch it at your leisure, right? So, and then if you have questions, you can message me and that type of thing, and we'll handle that in that way. There's just rules that we need to have certain number of contact hours per semester in terms of lectures and stuff. So we've got to be careful we actually make that class up. So I'll do that. And all right, one other thing, there's this guy out here, Ian, explains signals systems and digital communications. He's got a whole channel. This is a playlist. You may explore his channel. There's some really great lectures. I like him. I think he explains things really well, probably better than I do and stuff. So take a look at those. We're not going to cover all of these topics. There's, we're doing this in one lecture, and this would take several lectures to get through. All right, so let's go ahead and we rushed through spread spectrum technology a little bit, right? But so I just want to touch base on it real quick. Again, we talked about frequency hopping, and we did some math. I blitzed through this math really fast, and all, but looked at both slow hopping and fast hopping type of systems. Then we looked at direct sequence, which is where we take a modulated signal, and then we chop it with kind of a sequence of plus and minus ones typically, or maybe zeros and ones or something. And we chop it at a much faster rate than this is, right? So the bandwidth of a signal is related to its rate, right? So if this is going at let's say a megabit per second, that's roughly going to describe its bandwidth that it's going to consume in the channel, right? So that it has to do with the pulse shapes and that type of thing. But so if we're and exactly how we define bandwidth, but if this is going at 1 megabits per second, that's kind of defining its bandwidth out here in the channel. But now we chop it with something that's maybe 10 times as fast, or let's say 100 times as fast, so 100 megabits per second, then that signal now has all this fast moving stuff in it, and so its bandwidth has been expanded, right? And now it's more on the order of 10 megabits per 10 megahertz or 100 megahertz, depending upon how much faster this is than that, right? So we use these pseudo noise code generators, and they're basically in these shift registers, and we pull taps out of them at particular points and feed them back. So they're a linear feedback shift register. So this is going to have some length to it and some taps. They're summed in a modulo 2 manner and fed back into the input. And that will create a deterministic code that's defined by these taps and the length of the memory here, but one that has noise characteristics, right? And then you can change these taps to create different codes, right? So that's the origin of these things, and then that converts these codes into pulses, again, like a plus and minus pulse that will flip the phases of these things, and then we do the reciprocal operation here, right? So, and then I give you some examples. So CDMA, code division multiple access, is basically a way to use different codes here for different users or different cell stations, right? And then each code is roughly orthogonal to another. So if is just the nature of CDMA, that if I have these orthogonal sets of codes, if I try to despread the receive signal with a different code than it was spread with, I will not correlate well. And the result out here will basically look like noise, right? That's why we use these long pseudo noise type code generators, right? And so it'll look like noise here if I use a different code. Well, that is how we can separate out different users, right? So users would have one code that their communications would be spread and then despread with the same code. And we can transmit on the same channel in the same bandwidth a different code, but when a different user would try to despread that, it's just they're going to use their code to despread it, but it's the wrong code, right? So it's just going to look like noise. Now it does increase the noise, so it's interference, but it looks like noise, right? And so your signal to interference and noise ratio is going to degrade with lots of other users in this channel, but you still have a means of communicating with multiple users, right? There's a limit, but you can support multiple users. A whole lot more to it, obviously, but we'll limit it there. And then chirp spread spectrum is much more popular in radar systems, but is used in a few esoteric things like this LoRa. It's kind of a communication mostly for IoT, Internet of Things type of systems, and its range is on the order of a few miles, right? So it could cover a city with a few base stations, or maybe even one base station for a small city type of thing. So and there, instead of multiplying by sequence or frequency hopping thing, we're multiplying it by this chirp that is a single frequency, like a cosine, but its frequency is swept from low frequency to high in this case, or let's say 5 seconds. So there's a low frequency here. By the time it ends, it's a high frequency. So if we multiply that in a mixer by our modulated signal, then it gets spread out over that bandwidth and over this time. Then we would multiply by the inverse of that when we try to receive it. All right, so we covered that on Tuesday. Just a little bit of review here. I know it's still very high level, very fast, but we'll move on and look at fading channels. So we will cover time varying fading channels, ray tracing model, ray model, delay spread, coherence bandwidth. Actually, we're not doing things in this order. We cover empirical models a little bit earlier, I think. We'll see. So as we've talked about before, the optimal design of a communication system descends directly from a channel model. And in the beginning, we assumed, let's say, a perfect model. We added additive white Gaussian noise to make our channel model a little bit more sophisticated. We've looked at a few different things, and here we're going to get a little bit more sophisticated, right? So many of the techniques we studied so far intended to cope with the non-idealities of the channel. Now, in reality, every channel is unique, and it may be unique to a particular time, right? So, and then if we're in a mobile type situation, then the channel changes over time. So to design a broadly applicable channel, we need to rely on or resort to statistics, right? We've got to use probability theory and statistics to be able to model our channels, right? So we've let's see, consider techniques adapted to additive white Gaussian noise, band limited channels, and multipath fading channels. Practical for channels for modern mobile communications are time varying in their characteristics. Transceivers are mobile, and the scatterers can be mobile, right? So when we talked about this multipath fading, we say that, well, there's signals can reflect off of things and then still get to the receiver. But if whatever they're being reflected off of, we'll call that a scatterer, if that moves, then that path that signal takes to get to the receiver is going to change. So the channels are time varying in their characteristics. So we're going to simplify waves, right? So we know from applied electromagnetics course, I think 311, right, is, there's a wave, and it propagates away from, let's say, an antenna to get to, transmit antenna to get to a receive antenna, and that's a propagating wave. We might simplify that to a plain wave front, so it's easier to analyze instead of kind of the spherical wave front that it really is, right? But we're going to simplify it even more and just consider it just a ray, right? That we can draw using our vector type of mathematics and graphics, right? So we're going to simplify those. And Schnell's Descartes law, that's just the whole like refractive index type of thing that you do in optics. You probably studied in physics, maybe second semester physics. I don't know how many semesters you take in physics here, but high school or college level physics, you look at refraction of light through different media of refractive index, and you should have covered that in your applied electromagnetics course also, right? So that is technically governed by the Schnell's Descartes law. In our case, we're not going to get down really to that level. It's just that things reflect, and they reflect against the surface normal of that reflecting media, and maybe some penetrates in, but a lot reflects out. That's what we're interested in, and it reflects off at a particular angle. So rays can be shadowed or blocked by large structures, right? And in addition to a potential direct path, there exists this series of reflected rays. Depending upon the relative positions of the transmitter and the receiver and all these reflectors, some subset of rays combine at the receiver. Now, at let's see, we'll do finish this up. Each ray travels a different distance and therefore has a different delay, phase, and amplitude at the receiver, right? So the amplitude is affected a little bit by the distance, but it's also affected by the absorption of the scatterer, right? So not all of that energy gets reflected. Some is absorbed by that. And also, some of these are kind of rough type of structures. Like if you bounce off, let's say, a tree, it's got a lot of roughness associated with it, right? That's maybe the right size relative to the wavelength, so that really you're getting all sorts of different angles that are bouncing off of that, right? Depending upon the roughness of that. So, so even if it doesn't look like it's angled perfectly to come back to the receiver, there's a lot of roughness in these reflectors or scatterers, such that there is some energy that's going to meet that Snell's law and arrive back at the receiver. So all these rays then combine vectorially, with amplitude and phase in the receive antenna via superposition, right? So let's look at this. As a wave travels through a distance of a wavelength, its phase moves through 2 pi radians, or 360 degrees, right? So if it moves a fraction of a wavelength, it's going to move a fraction of 2 pi radians, or a fraction of 360 degrees. So wavelength is a function of frequency, right? So therefore, the phase of a ray at the receiver varies with respect to frequency and affects how it adds or cancels with the sum of the other rays. So at one frequency, okay, or wavelength, you're going through some number of wavelengths and some leftover fraction, right? When you go through this distance d, and where d is going to vary depending upon the ray, right? And at that particular frequency and wavelength, they may add, and you move a little bit off in frequency, and therefore a little bit different in wavelength, and therefore a different, partial fraction of that wavelength, then maybe they start to cancel, right? So it's a function of frequency. So let's look at some examples. I've talked about this concept a number of times, but we've got, let's say, a transmitting antenna and then a receive antenna out here at this distance, right? And so there's a straight line distance. Well, here we're accounting for an elevation change and also a lateral change here, right? So we calculate that distance. That remember, from geometry, the shortest distance between 2 points is a straight line. So that's the shortest physical distance, which is also going to be the shortest delay, right? But then here we're going to have a ground bounce, right? So here's the Earth here, and so we bounce off the Earth and reach the antenna here, right? Depending upon how tall you are, or where, how tall that antenna, the receive antenna is, this net, total path here is going to be, a little bit longer than this one, right? So, but we can have a more complex environment, and let's say look down at a system where we have a wall here and a wall there. We've got a transmitter here and a receiver here, and we've got things bouncing here and here. We've got a direct path. We'll add a few more paths and stuff. So, and in reality, this is top down, and so we've also got maybe a floor that we're bouncing off of. Maybe we have a ceiling that we're bouncing off of also, right? So there's maybe some other rays that are implied by these, right? So the point is we can get very complex pretty quickly, right? So let's look at the channel transfer function. So a single ray has a spreading loss as the electromagnetic wavefront spreads out in 2 dimensions as it travels towards the receiver, right? So you may have a certain antenna gain at the transmitter, but as it propagates, it's spreading out in two dimensions, right? And so your receiver only intersects, your receiver antenna only intersects a portion of that wavefront. So the farther away you are, the bigger that wavefront is, and a smaller fraction of that wavefront are you receiving with your fixed size receiver antenna. So that gives us a general downtrend, right, that we would experience even if we just had one ray, right? But here we've looked at 2 rays, and what we see is over a distance here, sometimes these rays add and sometimes they cancel. So and here this is attenuation over here, or the relative receive power versus transmit power, right? So it's basically its channel transfer function. And so we see that we're in some cases losing lots of energy. And if we happen to have our receiver right at this location, we're not going to get any sort of signal, right? It's minus 145 dB versus maybe our system might be designed to operate with minus 88 dB or something like that. But we're really seeing this much worse response. So this is a top thing we call, when we have structure like this, these are deep fades, and they're very narrow, fortunately. So we just need to move a little bit and we'll get our strong signal back. But you can be really unlucky, right? And so when we have structure like this, we call this fast fading. It's maybe more appropriate to talk about fast fading in a frequency domain. I think we have example plot of that in a few slides. So we can characterize our channel with an impulse function, right? So we can look at time, and this might be a direct path, and we get a nice strong signal at this delay here. But then we might get a weaker signal here, and a little while later, maybe a little bit stronger than that, but weaker than that one. And then the point is here, this time can be anything. It's not necessarily periodic. It's not likely to be periodic, right? But you characterize this. You go out and measure it, right? So you might have a transmitter that's putting out pulses, and then you've got a receiver that captures the signal in time, samples it, and looks where these energies show up in time. And that's going to characterize the impulse response of your channel. Now, this is going to be for a particular frequency and a particular space, right? Position in a spatial domain, right? If you move off, you might get something a little bit different, or you move far enough, you might get something radically different. But the number of these significant impulses is related to the number of scatterers that you would have in your environment. All right, so there's often a dominant ray from a line of sight propagation, and we'll call that Riceian type fading, sometimes spelled this way, but most of the time this way. And so you would have probably a direct line of sight, although it's just mathematically, it's when one ray is much larger than the others and dominates, right? So it typically comes from a direct path. And that's typical in rural situations, on the highway, maybe a broadcast station type of thing where the antenna is very high and above most other structures and reflectors and that type of thing. In other situations, there's no direct line of sight between the transmitter and the receiver, right? So I'm sitting here and I've got a mesh Wi-Fi system in my house. So my laptop is right next to the mesh repeater. So that's got a direct path right there. But there's no direct path from that mesh repeater back to the main base station that's hooked up to my modem. So that is going, it's getting there, but it's reflecting around and maybe propagating through some walls and whatnot. But that's probably going to be more described by Rayleigh fading. Right, so many scatters producing many rays, but no real dominant ray, right? And that's typical of indoor propagation or urban outdoor, like in a city like New York, where you have lots of buildings and urban canyons, we call them, right? So, all right, so let's look at these as an example. Here we've got an impulse response of a channel here in time, and so we're going to see that the overall strength of this signal that at the receiver, that's again the superposition of all these different rays, that's going to follow this Rayleigh distribution. And so it related to a Gaussian, and in fact this has origins, which if you watch that Ian does signals YouTube video, he goes through and kind of explains the origin of this distribution, but it basically is arises from a central limit theorem where we have lots of different paths that then kind of sum vectorially together at the receiver, and they're going to have different amplitudes and phases. Or you can look at that in the IQ domain, or real and imaginary plane, in more of a Cartesian type coordinate system. And so you'd have one Gaussian distribution that arises from the central limit theorem for the real component of the fading, and another one for the imaginary component of the fading. And there we make an assumption that they're independent of each other, and then we so we would multiply those together, but then project one on the real axis and one on the imaginary axis, and then we convert those to polar coordinates, and you ultimately get this. So this is Rayleigh fading arises when you have kind of a product or a combination of two independent Gaussian type functions, right? And so that's the case we have here. So these alphas, sometimes you'll see them as sigmas also, that come from the variance of the Gaussian process, right? And but here it's one-sided. So we have the exponential, and x here is the distance away from the source, and then this is describing the probability of the channel gain statistics, right? So how strong would the signal be at that location? And since we're going outwards, we can't. And we're going outwards from a central location, it's x is always going to be greater than 0. So this is a way to calculate the mean of that process and the variance of that process. Note that again, this is describing the gain, but if you looked at the phase, phase is going to produce a uniform distribution, as it often does, right? So there's no preference for 0 degrees versus 45 degrees versus whatever, right? So all right, then there's Riccian fading. Now Riccian fading involves modified Bessel functions. Not sure you've studied Bessel functions in any of your prior courses, so don't worry about it. They're super powerful for periodic type systems and other type of things. They're both the non-modified or the basic Bessel function and modified Bessel functions are very powerful for modeling engineering systems. This I then defines a modified Bessel function, and the 0 is the order of it or so. So that's parameterized. It could be 0, 1, 2, 3, 4, 5, that type of thing, right? So this is a rough plot of this as this dimension z here, or in this case, this is a parameter r and s. R is kind of handling that distance, right, from the transmitter. And so again, this is the probability distribution function of the resulting amplitude due to this type of Riccian fading. This S is basically kind of handling the means of the Gaussian processes that are associated with the reflected paths, right? And it arises from the Rayleigh portion of the fading. So in this case, all the Gaussian processes all have 0 mean. The Gaussian processes that give rise to this Rayleigh fading, but in this case, they no longer have 0 mean. And in fact, if these means are 0 and you plug that in, then it reduces to Rayleigh fading. Did I say that right? Yeah, I think so. So, all right. So don't worry about this. I'm just kind of putting it out there. Just know the difference between Rayleigh fading and Riccian fading. There's lots of other models associated with this, but there's also purely empirical models. And these, developed using measurement campaigns, and then you fit your results to the equations, right? So you might stick a reference transmitter in a particular location and then drive around with your measurement equipment and measure the signals and look at it in a certain environmental condition and for a certain frequency range. Right, and then you collect all that data, and then you try to fit it to some equations. Maybe some of these equations, the parameters might have some little bit of physical meaning, but other times you're just trying to fit it to some results, right? So this kind of originally goes back to Hata, who made a bunch of measurements in Tokyo, extremely urban city, and is being continually refined, being mainly funded by this cooperative coopération européenne dans le domaine de la recherche scientifique et technique. Right? So they tortuously come up with this COST acronym from this French phrase right there. And so if you look in communication literature or standards in particular, like a standard might reference the COST 231 HADA model, which is down here. It's a crazy, scary equation, but it's just some coefficients here, a function of frequency. I think some of these are like the height of the antennas and distance, and there's a distance right there, and all. And then, but ultimately, this crazy equation is going to give you the median path loss in dB. Right, so this is fitted, but there's still some parameters that you adapt to a particular application. And again, it's just an empirically derived model, and there's lots of these different ones. And so you got to determine: are you designing an urban system, a rural system, a system that's got to work indoors in a house, or a system that's got to work indoors in an office building, or an arena, or a market, or something like that, right? So, all right. So let's look at delay spread a little bit. So as we talked about, rays reach the receiver at different delays. The delay spread affects how easy it is to compensate or equalize the channel. So we did a little lecture and then MATLAB project on equalization, right? So you're going to maybe measure the channel. If the difference between the minimum delay and the maximum delay is really large, it's going to be harder to equalize to that channel. Right. So it also affects how short a symbol can be before that ISI or intersymbol interference becomes a problem due to this delay spread. Right. So, and here we've got some metrics for characterizing this. Right. So this AC of tau is this power delay profile. This would be measured, and then you punch it into this formula to calculate the RMS value of this delay spread. So not super important that you know this formula or how to use it, but just the idea that you're measuring it and then you're coming up with some sort of average. So the symbol duration, well, let me say it another way, right? So we like short symbols because that means that we're sending a symbol in a minimum amount of time, and we can send the next one and next one and next one, right? So that ups our capacity or our rate at which we're sending information. But that if we try to go too short in time, right? That's short in time, short in period means high frequency, right? So if we try to go too short in time, we're going to have ISI problems due to these delayed impulse responses, right? So how far back do I have to go? These signals are going to start to interfere with maybe the subsequent main symbol, right? So if we're trying to send out these symbols at a fast rate, but we've got a significant amount of power that's kind of at a delayed response, then not only do they maybe impact the original symbol, but they start to impact the next symbol and mess with its energy. So we can deal with that just by going to a longer symbol. It's not a very good trade-off. We want short symbols or a fast symbol rate. So it's important to understand this delay spread and its effect. So if we have, let's say, a symbol duration that's like 10 times as long as delay spread, we can kind of ignore ISI. We can assume that that's an ISI-free channel. All right, another way of looking at this is coherence bandwidth. It's the range of frequencies over which the fading is approximately flat. I think I promised you a chart of the response versus frequency, and I thought I had one in here, but it turns out it was versus time. But it looks similar in that over frequency, if you have different frequencies, in some cases your channel response will have a deep fade, and we'd like it to be flat. And all, we don't like these deep fades. So we define this coherence bandwidth. This is a range of frequencies over which the fading is approximately flat. So if our signal is 10 megahertz wide, every part of that signal is going to see about the same channel response, right? It's going to be flat. And so we can calculate a coherence bandwidth by taking 1 over this 2 pi, this tau RMS that we calculated in that previous slide. And so it's just, as we might expect, bandwidth is often, just a reciprocal of, in some way, in some form of time, right? So this means that a large delay spread leads to a narrow coherence bandwidth, meaning that the channel will have more closely spaced notches in time, in frequency and stuff. So the portion of that bandwidth that we can assume is relatively or approximately flat is smaller when we have more longer delay spreads, right? So if all of your arrays are bouncing off a very close reflectors, then that distance traveled is just a little bit longer than the other ones, right? But if you've got, let's say an outdoor situation and you're in near the Front Range of Colorado out west, right? And you've got the Great Plains, the prairie, and then boom, you got the mountains, the Rocky Mountains there, right? And so your signal is reflecting off of those mountains, and that may travel a whole lot farther, right? So just picking an example like that, right? So ultimately, as we explained in the previous slide, this is affecting the symbol rate. So this is an important concept, and what we'll study very soon is this orthogonal frequency division multiplexing. So starting from 4G, 5G, 6G, and we've been modulating our cell phone signals using this OFDM concept, primarily because what it does is it breaks up the wide bandwidth, let's say 10 megahertz or 20 megahertz waveform, into a bunch of different channels. And each of those subcarriers, we call them, or subchannels, the fading that it's seeing is fairly flat, right? Because they're very narrow, right? There might be 1,000 maybe 1024. They tend to follow powers of 2. 1024 subcarriers in a 10 megahertz signal, and each of those subcarriers then is pretty narrow, and the channel can be assumed to be fairly flat or coherent over that bandwidth. And so we're breaking it up. It's kind of like crudely speaking, it's a piecewise linear approximation. Don't take that mathematically, but it's similar type of concept, right? So we're breaking up this complex thing, and we're using a whole bunch of these different subchannels or subcarriers to deal with this fading type thing. And if we got a particularly deep fade on a particular subcarrier, we just don't use that subcarrier, right? So, all right, we'll talk more about that when we get to that lecture. So let's cover some mitigation techniques. So we've got to live with these nasty channels. So how do we cope with that, right? So one way is diversity. Multipath may seem bad, but we can sometimes take advantage of it to improve things. So in time, if a mobile system experiences a deep fade, it will likely correct itself shortly, right? So if we're moving through the spatial domain, then or the transmitter is, or the scatterers are, right? So we might suffer a particularly bad fade, but then we're moving, right? So things will change. The channel will change. It's a time varying channel. And so if we have a bad fade, well, we'll kind of take advantage of that error control coding we did with the channel coding with maybe forward error correction. We might interleave or permutate these redundant symbols, right? So if we've got a linear block coder or a convolutional coder, we might take those symbols that have this redundant information and move them around in the sequence that we're transmitting in a particular set pattern, right? So we'll scramble it. And what that does is that moves the redundant symbols far apart if they're in time. If they're right next to each other in time, as kind of naturally occurs when we go through the encoder, then if we're in a deep fade, well, it might wipe out all of those symbols, right? All those redundant symbols, and we're not going to be able to achieve our error correction that we'd hoped for. But if we move them around according to a set pattern, that then we can descramble at the receiver before we do the decoding, then there's a better likelihood that redundant symbol, one redundant symbol, won't suffer the same fade that another one will, right? So we separate them in time. In frequency, well, we can use spread spectrum. So we can spread that spectrum, and since this fading is frequency selective, then we'll have some energy well away from those fades in the frequency domain. And so even if a tiny portion of our bandwidth gets affected, it's the same type of consideration when we have a narrowband jammer, right? That when we despread our spread spectrum, then that fade now only accounts for a tiny fraction of the overall bandwidth of the system, right? So, and then another approach that is essentially taking advantage of diversity is a spatial type system. So we will have multiple input and output antennas. So when you look at a modern cell phone tower, you might see antennas pointing in 3 different directions. Those are different sectors, and we'll talk about that in a few lectures. But even in the same direction, they might be 2 to 4 antennas, or maybe even more. And some of your routers, Wi-Fi routers, will have multiple antennas sticking out of them, right? They might have 4 antennas. Or if you've got a drone and you're flying a drone with your remote controller, it might have 4 antennas on it. So what that does is when those antennas are just spaced a little bit relative to the wavelength, then that path from that antenna to the receiver versus another transmit antenna to the receiver, those are still going to see about the same reflections, but they're whether that reflection adds or cancels at the receiver antenna is going to be dependent upon that kind of small spacing of the antennas, the transmit antennas, and or the receive antennas, the same type of thing. So one path might be suffering a deep fade at that frequency and position, location, but the other antenna might create a path that doesn't experience that deep fade. So you can kind of choose the best of both worlds. It gets much more sophisticated in that. Again, we'll have a lecture on this MIMO, multiple input, multiple output antenna system. So, but there we're relying on some spatial diversity, right? So diversity in time, frequency, or space. Error control coding, as we talked about here in time. The raised cosine filter addresses ISI that can arise from these bad channels and that type of thing. We looked at equalization and how we might equalize that at the receiver. And again, this multiple input, multiple output kind of spatial system. So equalization, I kind of had this slide before I added that whole lecture on it, but so there's some techniques for equalization. We've already looked at those. All right, so now kind of start to wrap up here, the relevance, right? So the development process of a new communication system is often standards driven, right? So we develop standards so that different manufacturers can build their own version of a communication system and know that it will be interoperable or compatible with radios from other manufacturers, right? So when you go to the store and you buy a new Bluetooth headset or something, then you don't have to worry about is my laptop or my phone or my car using the same brand as this headset I'm buying? No, it's as long as it meets the Bluetooth standard, it will be interoperable, right? So these are standards driven, and but when we develop a standard, we've got to determine, as we're developing all these techniques in this communication system, what is that channel going to look like, right? So that's really kind of the fundamental or early stage in developing a new communication system or an evolution of the communication system, is an understanding of that channel and develop a model so we can build up some models and make sure that this communication system is going to support the data rates, the number of users over the spatial dimensions, and fit within the spectrum and the power constraints that we have, right? And to achieve some level of bit error performance that we ultimately need, right? Whether it's 10 to the minus fifth or 10 to the minus sixth errors, bit error rates, or whatever, right? So we will probably need several models to be able to cover different scenarios, right? So, for example, 5G covers several very different bands and operating modes with different goals, and we'll talk about that. Of course, we're used to, maybe in the old days, we wanted our cell phone systems to support voice communications. Now we're texting and we're browsing and we're playing using apps or that type of thing, right? So, but there's lots of other uses of 5G, and so each of those different use cases of 5G and at different bands, whether it's operating at I don't know 1.2 or 2.5 or 5 gigahertz or 700 megahertz, urban, indoor, rural, all these things, highway, all these things have different channel characteristics. So we need to design our system to handle all those situations. All right, so in summary, statistical channel models are needed to properly design and model a digital communication system. These models might arise kind of fundamentally, as we saw in Rayleigh or Ricean type fading, where we make some simplifications and treat the waves as rays and look at how they might combine. Or we just might make a whole bunch of measurements and fit some equations to it, right? So be more empirically driven. Different channels lend themselves to a different class of model, which ultimately still needs to be fitted, right? So we still got parameters in there that need to be fitted. This fast fading is a challenging environment to overcome, but we saw that we have some mitigation techniques. All right, so reminder, we don't have class on Tuesday, if I'm correct on that, and but we will have an assignment due Tuesday night or whatever. If you need that wellness day, then to be well, which is, I think, a great thing, just turn in your assignment on Monday. So again, it shouldn't be that hard. Make an appointment with me if you need some help. And if it turns out we need a little bit more time, that's not a big deal. I could be talked into moving it. Just want to keep the semester moving along. So, all right, have a great weekend, and we will see you next Friday.